Greetings from the City College of New York. My name is Warner Watts Berry, and welcome to lecture number 11 of ordinary differential equations, this time undetermined coefficients. So, what does that mean? Well, this can solve a differential equation of any order as long as it's homogeneous and looks little something like this. We've got a y prime prime plus b y prime plus cy. So then, what do we do in such a situation? Well, this does not actually have to be homogeneous. If it's homogeneous, the solution gets way simpler. But then, let's say this is some function, f of x. Then things get a little bit tricky. So let's look at an example. What if 3y prime prime plus 2y prime plus 1y, or just y, is equal to cosine x plus sine x? What do we do in this situation? Well, let's think about it. If this is giving us a cosine x and sine x at the end, that probably means that y is a trig function, because taking the derivative of cosine gives you sine and vice versa. I know there's a negative here, which means technically it loops around, but that's the strategy we're going to use here. We're going to assume that y is equal to some linear combination of cosines and sines. A cosine x plus b sine x. That way y prime is minus a sine x plus b cos x. And y double prime is going to be minus a cosine x minus b sine x. So that gives us minus 3a cos x minus 3b sine x minus 2a sine x, which I'm actually going to line up, plus 3b and 2b cosine x, and then plus a cosine x plus b sine x, which gives us that minus 2a, or 2b minus 2a, has to be equal to that one cosine that we see over here, and minus 2b minus 2a has to be equal to this one sine that we see over here. So what does that tell us? Well, that tells us that minus 2a is equal to 1 and b is equal to 0, or in other words, a is equal to minus 1/2 and b is equal to 0, which means y is equal to minus 1/2 cosine x. But we're not done, because in this case, we still need to know the homogeneous solution. That's right. While the solution we just got technically works out, we still also have to know the homogeneous solution to get the general form. What's the homogeneous solution? Well, it's the solution of the complementary equation 3y prime prime plus 2y prime plus y is equal to 0 instead of f of x, which was cosine x plus sine x in that case. In this case, all we have to do is use what we call the quadratic formula. So in this case, since it's 0, that means we probably have a polynomial that's degrading over time. Probably got a second degree polynomial over here, turns into a first degree polynomial, turns into a 0 degree polynomial. Or, you know something even better than that, e to the x. Why? Because once you take the derivative, it gives back itself again. What happens when we take e to the minus x? We get e to the minus x the first time, then minus e to the minus x the second time, and e to the minus x the third time. See the potential for canceling out and giving 0? So then we let this be a quadratic equation, and that's pretty easy to solve. Minus 2 plus minus the square root of 2 squared minus 12, 4ac, over 2a, and you might say, hey, wait a second, the discriminant is negative. This gives us an imaginary solution, but fear not, we can use Euler's theorem in order to help us out here. So this produces the 3. We've got minus 1 plus minus root rad 2I divided by 3. So then that means that our solution is e to the minus 1 plus minus rad 2I over 3. Now, how do we actually write that in terms of something cool? Well, according to Euler's theorem, this is just cosine of, this is just e times t. This is just e to the minus 1/3 t, which is that real part, times cosine of rad 2 over 3 t plus sine rad 2 over 3t. And it can be plus minus sine, but this is all accounted for if we just say this is C1 and this is C2, which gives us some constants to work with. So that means that our actual solution, our general one, is minus 1/2 cosine x plus e to the minus 1/3 x times C1 cosine rad 2 over 3x plus C2 sine rad 2 over 3x. That's it. Thank you everybody for watching.
What do you see?
Sand.
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.
Integrals, infinite series.
I've never seen anything like them. From an Indian